once in a while it's advantageous to add a couple series together. Although if you add series together, your interval of convergence might get tainted. And just as an example, let's say that we have the first series. I'll make that red. The series with the a sub n inside. And then the second series, we'll say that the sum n there is a b sub n. And let's say that we knew their intervals of convergence. Let's say that the first one converged between -4 and +7, including -4. And the other one converged between -1 and 9. Well, if we're going to add them together to make a new series, a plus b, we have to be careful that we don't include parts that it may not converge on. So we have to take the intersection. So again, between -4 and 7, if I do a quick number line, just as a visual, here's -4, here's +7, here's -1, here's +9. Okay, not to scale necessarily, but that's okay. The red converges between -4 and +7. Notice the open and closed circles. And the green converges between -1 and +9. So it only makes sense that if you were going to add them together, the only place that the sum would truly converge would be here, in this region where they overlap between -1 and 7. And even though it says recheck the endpoints, I have yet to run into a situation where they've changed. I'm just saying. So the interval of convergence here between a sub n plus b sub n, that summation is -1,7. All right, that leads us perfectly into number 8. We want to find a power series for this. It's centered at 0, which makes me happy. But unlike the last few that we've done, this one's not geometric today. This is not geometric at all, clearly. Oh, man. You know what I could do? We haven't done this in a while, but I could factor the denominator into x minus 4 and x plus 2. And that will allow me to rewrite this thing in terms of partial fractions. Oh my gosh. Never goes away, does it? All right, I would like a common denominator. So I know I need a pair of x plus 2's on this. There we go. And on the next parentheses, I need a pair of x minus 4's, both in the numerator and denominator. All right, as you can see, all three denominators are now common, which means the numerators must match. So here's that equation. Now, since 5x minus 8 is not a constant, I know that a and b will not be opposite of each other. I'm going to let x equal 4, that'll give me the a, and I'll turn around and let x equal -2, that'll give me the b. All right, if x is 4, then this becomes a 0, which actually knocks this whole thing out. I get 6a equals, and if I put the 4 on the right, I get 20 minus 8, which is 12. So obviously if 6a is 12, then a must be 2. All right, very good. Next, we'll find b by making x -2. And if x is -2, then this part becomes a 0. You get a times 0. Plugging the -2 in will give you -6b equals, and on the right side it'd be -10 minus another 8, -18. And since -6b equals -18, b will be +3. All right, so a is 2, b is 3. Let me get rid of the red stuff. And I'll replace the a and the b with a 2 and a 3. All right, at this point, I can see the opportunity to make two separate geometric series out of this, because they're starting to look like what they did in the first couple of days of section 9.9. I think I can pull this off. I am going to need a little bit of room though, so. Okay, so f of x instead of being equal to this, which was really hard to deal with, I now have the right-hand side. Let me rewrite this on the fly. So that's going to be 4 minus x down below. And I'll have to make it a negative 2 up top since I switched the order. And I'm going to go plus 3. I'll switch the order of the denominator to 2 plus x. That won't require me to do anything different. All right, that looks pretty good. Let's proceed. For these to go truly geometric, both of these numbers have to become 1s. So I have to do some division. It's probably also a good time to start color coding. So this one I'm going to make red, and then the next one will turn green. All right, on the red fraction, I have to divide everything by 4 because, again, I must have this 1. So this becomes x over 4. The top becomes negative 1/2. All right, that looks good. For the green part, we have to divide everything by 2, so that'll be a 1. That'll be an x over 2. And that'll be a 3/2. But remember, this needs to be a minus, so I'm going to say 1 minus negative x over 2. So that way it's ready to go. Both red and green now are in true geometric format. So now I can turn it into a power series like the directions asked me to. All right, with the red, we have term 1 being negative 1/2. I'll write that first. And then we have r being this 1/4 x, or x over 4. And that's taken to the n power. With the green, term 1 is 3/2. R is negative 1/2 x, or negative x over 2. And that's going to go to the n. And that's going to be what we need. All right, so we found a power series for the function f of x centered at c. It's down in that box in the corner. Now we need to find the interval of convergence. And that's going to be the intersection between the two intervals of convergence between red and green. For the red part, your interval of convergence is going to be from negative 4 to positive 4. Because r, the x over 4, has to stay between 1 and negative 1. If you put a positive 4 into this, you can see that would be your 1. If you put the negative 4 in, it would be negative 1. So that's going to be that one. For the green, your interval of convergence is going to be negative 2 to positive 2 for the same reason. We want to take the intersection between these two. And I think you can see that the intersection between them is just this. Negative 4 and positive 4 reaches out farther to the left and to the right than negative 2 does. So to play it safe, the official interval of convergence is going to be x has to stay between negative 2 and positive 2. And since both red and green were geometric, we don't have to test the endpoints. That is it. All right, number 9, we're given a Maclaurin series, and part A, we're asked to find the interval of convergence for it. So obviously we want to use the ratio test here. And as always, we can use L'Hopital's rule or L'Hospital's rule and do some canceling. So we've got a pair of 1s there, and we're going to end up with an extra 3x in the numerator. And that's all that we're going to have left, so this will end up being 3x. Since we want this to converge, it's going to be less than 1, which means 3x will be between 1 and negative 1, and therefore x will be between negative 1/3 and positive 1/3. And of course, this represents the unofficial answer for the interval of convergence, because we do have to test the endpoints. I'm probably going to need a little bit of room to do this, so I'm going to start fresh with a clean slate here. Okay, let's test the endpoints. When x is negative 1/3, I'll do that part in red, and you bring the negative 1/3 up here, that's going to end up being negative 1 to the n plus 2. So we're going to end up with an alternating component there. And you can
tell right away that that's going to converge by AST. Of course, you have to make sure that the sum and the a sub n part of it is decreasing and heading towards a limit of 0 as n approaches infinity. It is. All right, let's try the other one. I'll use green this time. We're going to let x be positive 1/3. That's just going to give us 1 to the n plus 2, which is simply 1. You have to use limit comparison test here. You would compare it with 1 over n, which is obviously a diverging harmonic p-series. When you run it through the limit comparison test, and you end up multiplying by b sub n's reciprocal, it's going to come out to be 1. And 1 is a number that is positive and finite, and so a sub n and b sub n behave the same way. Since 1 over n diverges, 1 over n plus 2 will also diverge. Therefore, we're going to have a right endpoint that is curly and not included at 1/3. Therefore, our final answer up here in magenta, we have to put a little equal to on the negative 1/3 because that converges, but the positive 1/3 diverges, so we'll leave that alone. And that is the official interval of convergence. Again, if you're into interval notation, you can also write it like this, and that would be equally fine. All right, for part B, we want the first 4 terms and the general term for f prime of x and its Maclaurin series. Well, I'm going to go ahead and just go term by term. Since f of x is given to us, we'll just take the derivative of each one, starting with this 9/2 x squared. And the derivative there, of course, the 2's will cancel, will just be 9x. All right, next up, the second term, the 3's will cancel out, and we're going to have 27x squared plus 81x to the 3rd. And I'm beginning to see the pattern now here. Each term we're multiplying by 3x, which makes sense because we saw that in part A. So if I multiply by 3x one more time, let's see, 81 times 3 is going to be 243. X to the 4th. So those are our first 4 terms. And the general term is going to have an x to the n. And let's see, 9 was 3 squared. 27 was 3 to the 3rd. This is going to be 3 to the something. I'm just going to pick out a random term. How about this 3rd term? The 3rd term is x to the 3rd. That's why the nth term would be x to the n. But 81 is 3 to the 4th. Therefore, it's going to be 3 to the x plus 1. It's always 1 power higher, 3, than what the x has. So that's going to be my general term for the Maclaurin series. All right, part C, we want to use the Maclaurin series that we just found to find the value of f prime of 1/9. Okay, I've pasted my answer from part B. And again, we realized it was geometric. I know that term 1 is this 9x. And I also know that r, the thing that we're multiplying by each time, is 3x. So I have everything that I need. So f prime of 1/9 is simply going to be the sum of this infinite geometric series. Term 1, we use our formula, the tried and true formula, over 1 minus r. And we'll simply change the x's to 1/9. I already did it over here on the left-hand side. Now I'm going to go ahead and do it on the right-hand side as well. Okay, let me simplify this. The numerator will simply be a 1. The denominator is 1 minus 3/9. That's the same thing as 1 minus 1/3. So the answer is 1 over 2/3, which happens to be 3/2 or 1.5. And that's it for the entire section on geometric power series, including operations with power series. So nice job, and we'll see you next time.